Dear students, welcome. Today we are going to dive deep into one of the most important yet most often misunderstood topics in the computational fluid dynamics, which is the difference between the conserved and the unconserved forms of the Navier-Stokes equations. If you have ever run a CFD simulation that blew up for no reason, no obvious reason, or saw a shock wave move at a wrong speed, or noticed your total mass slowly drifting over the time, you may have been bitten by the wrong choice of the equation form. So by the end of this session, you would be understanding exactly why that happens, and more importantly, how to choose the right form for your application. So let us start with the absolute foundation. The Navier-Stokes equations are not just arbitrary differential equations. They are the mathematical statement of the three fundamental physical laws: the conservation of mass, conservation of momentum, and conservation of energy. So by conservation of mass, we mean mass is neither created nor destroyed. Conservation of momentum is linked to the Newton's second law, F is equal to ma applied to a fluid, and conservation of energy is related to the first law of thermodynamics. These are the universal truths. By the way we write them mathematically can take two very different forms: the conservative or the divergence form, and the non-conservative or the convective form. So here is the key insight that will guide our entire discussion. For a perfectly smooth continuous flow, both forms are mathematically equivalent. You can derive one form from the another using the chain rule or the continuity equation. So why should we care? Because in CFD, we never deal with perfect continuous flows. We work on discrete grids with finite precision and often with discontinuities like shocks. And in that discrete world, the two forms behave very differently. So let us set our goal for today. By the time we finish, you will be able to recognize the conservative and the non-conservative forms at a glance, explain why the conservative form is essential for the compressible flow with the shocks, and understand the Lex Ventroph theorem, a name you should remember. And lastly, decide for your own simulations which form to use and which numerical method is the best, fits the best. So let us begin with the mathematics. To understand the difference, we have to go back to the control volume approach. Imagine a tiny box fixed in space with fluid flowing through it. This is the Eulerian perspective. So we are not following individual particles. We are watching what passes through a fixed region. The conservative form comes directly from a balance over this that particular fixed box. For any conserved quantity, say mass, momentum, or energy, the rate of change inside the box equals the net flux crossing the boundary plus any sources. Mathematically, for a journal conserved variable u, we can write this particular equation here. U is the vector of the conservative variables: density, momentum, and total energy. And the f of u is actually the flux tensor. So it includes the convective flux, which is rho u times the velocity, and the diffusive flux, which is the viscous stress and the heat conduction. Whereas S is any source term like gravity. Now notice this structure: the time derivative plus the divergence of a flux. That divergence is the key. When we integrate this equation over the finite volume and apply the Gauss divergence theorem, the flux term becomes the surface integral. That means the change inside the volume depends only on what crosses its boundaries. This is the global conservation, and it is built into the mathematics. Now, how do we get the non-conservative form? So the answer to this is that we normally expand the divergence using the product rule. And for the momentum equation, we, for example, the convective term, the divergence of rho u u becomes u times divergence of rho times u plus rho u divergence of u. So uh, then we use the continuity equation to eliminate the um, the operator times rho times u term, and after some algebra the momentum equation becomes as displayed. So this is the non-conservative form, often written with the material derivative d over dt, and it actually looks simpler. It directly says the mass times acceleration equals to the forces, but look carefully, the divergence of the flux term here has disappeared, replaced by the additive derivatives. So the difference is not about physics. Both forms represent the same physics. The difference is actually about what is being differentiated. In conservative form, we differentiate the fluxes, while in the non-conservative form, we differentiate the flow variables themselves. That apparently small change has huge consequences when we go to a computer. Now, let me give you a simple analogy. Suppose you have a bank account. The conservative form says the change in your balance equals to deposits minus the withdrawals. The non-conservative form might say that the rate of change equals your spending rate times some factor. Both are true if you do the algebra exactly, but if you only check your balance once a day, or if you round off any transaction, the conservative method will always keep the total correct, because it directly accounts for what crosses the boundary. The non-conservative method, on the other hand, might lose a few pennies here and there. If in CFD, those pennies are mass, momentum, and energy. Now let us see why the conservative form is so powerful in numerical simulations. The key is what we call the telescoping property, also known as the summation by parts property. Imagine we divide our domain into many small cells, like a finite volume mesh. In a finite volume method, we store the average value of u inside each cell. Then we compute the flux of u across each face of the cell, and the update of the cell I is given by this particular equation. So here f subscript I plus half is the flux leaving the cell I through the right face and entering the cell I plus 1. Now, here is the magic. If we sum the updates for all cells from I equals to 1 to I equals to n, what happens? The flux at point I plus half appears once with a plus sign from a cell I, and once with a minus sign from the cell I plus 1. They cancel exactly. The only terms that remain are the fluxes at the very boundaries of the whole domain, which is hereby represented. Now that means the total amount of u in the entire region changes only because of the flux through the outer boundaries. No matter how coarse your grid is, no matter how large your time step is, the conservative scheme guarantees that the mass, momentum, and energy are conserved globally up to the machine precision. This is not a coincidence, it's a direct consequence of writing the equations in divergence form and using a numerical method that respects that structure. The finite volume method does exactly that. Now, what happens if you use the non-conservative form? You would discretize something like rho u partial u by partial of x. There is no flux to cancel. When you sum over all the cells, you get a bunch of terms that do not necessarily sum to zero, so the global conservation is not guaranteed. In many cases, the error might be very small, but for problems with shocks or long simulation times, it can accumulate and destroy the physical integrity of your solution. So let me give you a concrete example. Suppose you simulate a simple shock tube. Um, Tube with high pressure on the left, low pressure on the right. The conservative scheme will get the shock speed correct, while the non-conservative scheme, even with a very fine mesh, may produce a shock that moves too fast or too slow, or it may add or remove mass from the tube. I have seen simulations where the total mass drifted by 5% over a few thousand time steps, completely unacceptable. So the telescoping property is not just a neat mathematical trick, it's a foundation of reliable CFD for compressible flows. Now we come to the most important theoretical results in this area, which is the Lex-Ventroff theorem. This particular theorem provided by Lex and Ventroff, proved by Peter Lex and Burton Ventroff in 1960, uh, tells us exactly which numerical method or the scheme converges to the correct physical solution when shocks are present. First, let us understand the problem. The Navier-Stokes equations are partial differential equations that assume the flow is smooth and differentiable. But a shock wave is a discontinuity, density, velocity, and pressure jump across an infinitely thin surface. At that surface, the derivatives do not exist. So, in a strict mathematical sense, the differential form of the equations break down. However, we know that shocks are real physical phenomena. So, how do we handle them? We go back to the integral form of the conservation laws, the same integral form that comes from the conservative differential equation. Across a shock, the integral form is still valid and it gives the Rankine Hugenoid jump conditions. So those conditions tell you exactly how much density, velocity, and pressure changes across a shock, and they determine the shock speed too. Now here is what the Lex-Ventroff theorem actually says. It says that if a numerical scheme is consistent with the conservative form of the equations, and if the scheme is conservative, meaning it updates the solution using the fluxes, then as a grid is refined, any convergent sequence of numerical solutions will converge to a weak solution of the conservation laws. That is a solution that satisfies the integral form and therefore the correct shock jumps. Now, this particular theorem also has a negative side. If your scheme is not conservative, it may converge, but it could converge to a wrong weak solution. The shock might have the wrong strength or the wrong speed, and you will not know it because the solution will look smooth and reasonable. Let me repeat that because it is crucial. A non-conservative scheme can look perfectly fine, converge as you refine the mesh, but still give you physically incorrect shock speeds. That is a nightmare scenario for an engineer. So the practical rule is very simple. If your flow has any shock waves, even weak ones, you must use the conservative form. Not because the non-conservative form is always wrong, but because you have no guarantee that it is right. The conservative form would give you that guarantee thanks to Lex and Vendroff for the Lex-Vendroff theorem. So this is why all commercial and open source codes for compressible flow like Fluent, OpenForm, SU2 use the conservative form for the Euler and the Navier-Stokes equations. So they may also allow a non-conservative option for special ones, special cases, but the default is conservative. Now we have talked about the equation forms. Now let us connect them to the numerical methods you actually use in the CFD: the finite difference, the finite volume, and the finite element. The finite volume method, which is abbreviated as FVM, is the natural home for the conservative form. In fact, FVM is derived from the integral conservation law. You start by dividing the domain into the control volumes. You integrate the conservative equation over each volume. The divergence becomes a surface integral of the flux. Then you approximate that flux on each face. Because of this, any finite volume scheme is automatically conservative, provided you use them on you use the same flux on both sides of each flux. That is why finite volume method actually dominates the compressible flow, CFD, turbomachinery, and aerodynamics. The second is the finite difference method, FDM. This method works directly with the differential form. You may apply the FDM to the conservative form. You just discretize the divergence form using the difference formula. For example, This is the flux difference scheme equation represented over here. So if you do not consistently so if you do that consistently, you can actually achieve conservation. However, many simple FDM codes discretize the non-conservative form directly because it is easier to code, and that is dangerous for the shocks actually. So if you use the FDM approach, make sure you are using a conservative flux differencing formulation. Then there comes the uh, method called as a finite element method, FEM. Traditionally, FEM is based on the weak form and is not inherently conservative. The weak form is derived by multiplying the equation by a test function and integrating by parts. So that integration by parts moves a derivative onto a test function, and the boundary terms give the flux. So because the test function is not constant, the cancellation of the internal fluxes is not guaranteed. That said, modern techniques like discontinuous Glerkin, which is often abbreviated as DG method, have been developed specifically to restore the conservation. In DG method, you allow the solution to be discontinuous between the elements, and you actually enforce a numerical flux at the interfaces, exactly like the finite volume. But the DG method are now very popular for high order simulations of shocks and turbulence because they combine the accuracy of FEM and with the conservation of FVM. So a quick summary over here is that the FVM is conservative by design. Use it for the compressible shock capturing flows, while FDM can be conservative if you use for the flux differencing. Avoid the non-conservative form for the shocks. And lastly, FEM, traditional forms are not conservative. Use the DG method or other conservative variants for the shocks. And remember that the choice of numerical method is not the same as the choice of the equation form. You can write the finite volume code for the non-conservative form, but that would be like owning a race car and driving it in the first gear. So do not do it. So far, I have very emphasized on the conservative form for compressible flows like with the shocks. But what about the incompressible flows like water in a pipe or air around a car at low speed? So here the situation is very different. In incompressible flow, the density is constant. The continuity equation reduces to the gradient of u equals to zero. There are no shocks because the speed of sound is infinite. Information travels instantly, and the pressure adjusts to keep the flow divergence free. So the main reason for using the conservative form is capturing the discontinuities as it would disappear after within a few seconds. So as a result, many incompressible CFD codes use the non-conservative form of the momentum equations, often written as displayed over here, plus the divergence free condition. So this is the form you see in most textbooks on incompressible flow. The finite difference and finite element methods work well with this form for laminar and turbulent flows, provided the grid is smooth and the time step is reasonable. However, and this is important, even for incompressible flows, the conservative form has advantages for long time integration and for large eddy simulation LES of turbulence. Why? Because the non-conservative form we have what is called aliasing errors, errors that come from the products of two numerical approximations. So these errors can artificially add or remove the kinetic energy, and which is bad for turbulence. The conservative form, by maintaining global momentum balance, tends to be more stable over long simulations. So my recommendation is that if you are doing steady low Reynolds incompressible flow type simulation, the non-conservative form is fine. If you are doing the high Reynolds turbulent or very long unsteady simulations, lean forward the conservative form, or at least a skew symmetric form, which we will discuss in a few minutes. One more nuance is that some incompressible algorithms, like the projection method, are derived from the conservative form. They split the velocity update into a predictor step using the conservative momentum equation without pressure, and a corrector step that enforces the divergence free. So even for incompressible flow, the conservative form appears under the hood. Now, let me introduce the two advanced concepts that you may encounter in high fidelity CFD applications, like the skew symmetric form and the kinetic energy preserving KEP schemes. Remember the non-conservative advection term, the conservative advection term. So they are mathematically equivalent, but there is a third way, which is called as a skew symmetric form. So why would anyone use that? Because in the continuous world, the this particular form exactly conserves kinetic energy when the flow is inviscid and incompressible. The conservative form also conserves the kinetic energy, but the non-conservative form does not, because the product rule expansion hides the energy balance. In discrete form, however, the standard conservative schemes do not conserve kinetic energy exactly. They actually conserve the momentum and mass, but kinetic energy can be lost due to numerical errors. This loss of kinetic energy acts like an extra viscosity, which can be problematic for under-resolved turbulence simulations. So enter the kinetic energy preserving KEP schemes. They These schemes are specially constructed discretizations using finite difference or finite volume that ensures the discrete advection term does not create or destroy the kinetic energy. So they are often based on the skew schematic form. KEP schemes are widely used mostly in direct numerical simulations DNS, or large eddy simulations LES of turbulence, where you want to minimize the numerical dissipation. So you now have a spectrum, and we would be summarizing the non-conservative form, conservative, and the skew metric or the KEP forms. So non-conservative form is simple but does not conserve anything discrete, while on the other hand, a conservative form conserve the mass, momentum, energy, but not necessarily the kinetic energy. uh, and the new or the advanced scheme is the skew symmetric or the KEP scheme, which actually conserves the kinetic energy on top of everything else at the cost of more complex coding. So for most of the engineering applications, the standard conservative form is sufficient. For cutting edge turbulence research, KEP schemes are the gold standard. Now, moving on to this particular segment is for those of you who use finite element methods. The weak form is the different way of writing the equation, not by discretizing the derivatives directly, but by multiplying by a test function and integrating over the domain. So for a conservative form, the weak form looks like as displayed, and this integration by parts moves the uh, divergence from the flux onto a test function, and the boundary term appears. So this boundary term is exactly the flux through the domain boundary. Now, if you use the continuous Glerkin or the standard FEM method over here, the test functions are continuous across the element boundaries, and the internal boundary terms cancel only if the flux is continuous, which it is for the smooth flows. But for the shocks, if the flux is not continuous and the cancellation fails, that is why the standard FEM struggles with the shocks. Discontinuous Glerkin method, on the other hand, fixes this. In DG method, the test functions are discontinuous between the elements. You get a boundary integral on every internal phase. You then replace the flux on that phase with a numerical flux function, exactly like in the finite volume. So this restores conservation locally on the each element and globally also. DG is essentially a hybrid of finite volume and finite element. It would give the high order accuracy and conservation, making it very powerful for the compressible flows like with the shocks. So if you are working with the working in the finite element method, remember, for conservation, think of the discrete Galerkin method or the continuous Galerkin method too. So let us bring everything together into a practical decision tree. Imagine if you are about to start a new CFD simulation. Ask yourself three questions. These questions: that does your flow contain the shock waves or the strong discontinuities? If yes, you must use the conservative form. No exceptions. This includes the supersonic or the hypersonic aerodynamics, detonations, blast waves, and even some high-speed internal flows. Second question you must ask is the flow compressible but without the shocks? For example, the subsonic compressible flow in a nozzle, smooth, no shocks. The conservative form is still highly recommended over here, but because it handles the density variations correctly, many codes default to conservative for compressible flow regardless. The third question which you must ask is the flow incompressible. Is the flow incompressible and steady? Then the non-conservative form is acceptable, especially if you are using a well-validated incompressible solver. But be aware of the limitations too. And then you must also ask that, are you performing a long time integration, many flow through times, or a turbulent flow simulation? So then lean forward to conservative or skew schematic forms to avoid the drift or energy errors. And lastly, you must also ask that what numerical method is your solver using. Either it's a finite volume, which almost certainly conservative, you are safe in that particular case. But when you are using the finite difference, check the manual. Look for the words like the flux differencing or the conservative. And while you are using the finite element method, check if it's the DG or the continuous Galerkin method. DG method is actually conservative and continuous Galerkin method may not be. So here is a simple rule of thumb: when in doubt, use the conservative form. It is always physically correct, it is numerically robust, and it protects you from the hidden errors. So the only downsides are slightly more complicated code and a small increase in computational cost, but those are trivial compared to getting the wrong answer. So even with the best intentions, things can go wrong. Let me share the three common pitfalls you when you when using the wrong form, and how to recognize them. The first one is the moving shock. You simulate a shock tube or or a supersonic inlet. The shock location from your simulation does not match with the theoretical value, and refining the mesh does not help even. Or the shock moves at a wrong speed. So this is the classical symptom of the non-conservative scheme. The Lex Ventroph theorem says it can converge to a wrong weak solution. How to fix it? Switch to a conservative scheme in this particular case. The second is the drifting totals. You are running a long simulation of a closed system. For example, no mass through the boundaries. You monitor the total mass or the total energy, or over thousands of time steps you see a small drift, say 1% per 10,000 time steps. That drift is almost certainly due to the lack of conservation. With a conservative scheme, the total should remain constant to within the machine round of about 1 exponent minus 15 relative. If you see drift, check if your scheme is truly conservative. Also check for bugs in flux calculations. And lastly, the spurious oscillations near the shocks. You capture a shock, but you see wiggles, oscillations up and down just before and after the shock. So this is the Gibbs phenomena. It does not necessarily mean your scheme is non-conservative, but even conservative higher order schemes can oscillate. But if you see oscillations and the shock speed is wrong, that is strong indicator of the non-conservation. The fix is to use the conservative scheme with some form of limiting or artificial viscosity like a TVD, which is often abbreviated as total variation diminishing scheme. So let me also mention a suitable pitfall over here, which is the inconsistent flux linearization. Some implicit codes linearize the flux for the Newton solver. If the linearization does not exactly match the flux function, you can lose the conservation even if the base scheme is conservative. Always verify that your Jacobian is consistent with your flux. Finally, a debugging tip is that run a simple 1D shock tube problem. The short shock tube is a standard one. Compare your density, velocity, and pressure profiles to the exact Riemann solution. So if your shock location is off by more than 1 to 2% on a fine mesh, something is wrong over here. This test should be a part of your code validation. Now, we have covered a lot of the ground. Let me summarize the key topics. Number one, the Navier-Stokes equations have two mathematically equivalent forms, which is the conservative divergence and the non-conservative, which is the advective form. So they are equivalent for the smooth flows, but not for the discontinuities like the shocks. The second one is that the conservative form directly expresses the global conservation laws when discretized by a finite volume method or a conservative finite difference scheme. So it guarantees that mass, momentum, and energy are conserved globally, that which is the telescoping property. The third is that for flows with shock waves, that conservative form is mandatory. The Lex-Ventropf theorem proves that only conservative schemes are guaranteed to converge to the correct weak solution with the right shock jumps. Non-conservative schemes, on the other hand, can converge to the wrong solutions. The four is that for incompressible smooth flows, the non-conservative form is often acceptable, but the conservative or skew symmetric forms are safer for longer or turbulent simulations. Fifth, or the second last one, is that the choice of numerical method matters most. Finite volume is naturally conservative. Finite difference can be made conservative, but traditional finite element is not conservative at all. Discontinued, discontinuous Galerkin is conservative. Lastly, we must be aware of the pitfalls, drifting totals, wrong shock speeds, and spurious oscillations. Use the sword shock tube test to validate your scheme. Now, I want to leave you with a broader perspective. CFD is a tool for understanding the physics and making engineering decisions. The equations we solve are not just symbols on a page, they represent real mass, real momentum, and real energy. So, when we use a non conservative form, we are essentially telling the computer to ignore those global balances. Sometimes that is fine, but when it matters, when lives depend upon rocket nozzle design, or when an aircraft safety margin is at stake, we must respect the physics. The conservative form is a way of respecting that physics. So, as you go back to your work, I encourage you to look at your own simulation setups, open your solver manuals, find out which form it uses by default, and if it gives you a choice, understand the consequences. Run a simple 1D shock test to convince yourself, and never assume that a fine mesh will fix a fundamentally non-conservative scheme. The Lex-Ventropf theorem tells us that even in the limit of infinite resolution, the wrong answer may persist. So thank you so much for your attention. I hope this detailed discussion gives you a confidence in choosing and using the correct form of the Navier-Stokes equation in your CFD work. I am happy to take the questions, or you can review the slides and references provided. Thank you.